Okay, I think that we are ready to start. So, welcome everybody to my talk about Speck flavored streaming microservices with Akka. Before we start, two words about me. My name is Andrea Zito. Usually on the internet, you can find me with the handle Nivox. Up until last week, I was a senior software engineer at Thinking, where I mostly work on streaming sensor data, computation pipeline, and microservices. But actually, starting from this week, I am now a Scala developer at commercetool. There you can see my website where you can find like one single blog post and nothing more, but maybe in the future I will put some more context. Okay, so what do I mean by Speck flavored? Well, in this talk, I'm gonna speak to you about Spekka, which is an open source project that I built, gathering the experience that I got from working at Thinking, doing microservices and handling streaming data. Spekka is actually just stands for Streaming Productivity Enhancements for Akka, but this is just a retrofitted acronym to make it sound like Speck, which is a typical meat product of my region of Italy, which is like bacon. Okay, so what do I mean by streaming microservice? Microservice is already kind of a loose term, and putting in front of it streaming doesn't really clear up the situation. So let's pinpoint some of the key things that I have in mind when I talk about streaming microservices. For starters, I think that a streaming microservices is some process program that reads data from a streaming source. Then it performs some computation, possibly exposing some API to interact with this computation. And probably it will also generate some kind of output, probably to some other streaming source that will be read then by other streaming microservices down the pipeline. Okay, then what are the desired properties that I have in mind when I speak about streaming microservices? Well, for starters, I would like them to be resilient, so meaning that they need to be able to recover from failures. I would like them to be scalable, meaning that they should be able to adapt to the amount of data that we throw at them. And I would like them to have exactly one semantic. Now, exactly one semantic is kind of a touchy topic. In my mind, when we talk about exactly one semantics, we are basically telling a lie. And what I mean by that is that all the frameworks and library that advertise that they have exactly once as a feature, they only can guarantee that when you stay inside the constraints that library puts on you. And whenever you try to go outside those constraints by doing some kind of side effects, for instance, writing to a Kafka topic and writing on the database, and this is not something that the core library supports, then you lose this exactly once property. But then what we can do? What we can actually do is support at least once. That is a much simpler guarantee to support. And then we can have like an idempotent logic inside our microservices, or instead exploit input dead application. And in this way, we end up with what is called effectively once. This is not an exactly one system, but from an external observer of our system, they will not notice any difference with respect to an exactly one system. Okay, so this is kind of like the typical architecture that I have in mind when I'm talking about streaming microservices. They are characterized by having this durable queue. In my case, in my experience, this was a Kafka. And then all these microservices read data and write data to this durable queue, probably on different topics. They have a dedicated storage layer that they can use to save their state if they are stateful flows. And then they probably have a dedicated API layer which they can use to expose some REST API that interact with that state. Okay, so what is the run loop that I have in mind for these microservices? Well, first, the program obviously reads data from the durable queue and also the context. In this case, the context is something that is related to that piece of data, and we can use to know when that data has been processed. In the case of Kafka, this would be the offset. At this point, we are going to process the data, but we want to keep the relationship to the context of the input message. Then we can produce some output as side effect, like writing to another topic on Kafka. We can then persist the state if we are a stateful service. And then we can mark the context as done. In Kafka world, this would be the committing of the offset. Now, it's important that the order of the operation are performed in this order, meaning that we before produce output as side effect and only then persist the state. And only after that we do the committing of the offset. This is because if we were to crash if we were to save the state before producing the output, and we were to crash right after it, our program would resume reading from where it left off, thanks to Kafka and the offset. But at this point when we process the same input message, our state would be different. And so we could end up not producing the same kind of output or not producing any output at all. So in order to maintain the at least once guarantee, it's important that we perform this operation in this order. Okay, so now let's start to go inside a little bit in this work. As I've hinted in the title, in this presentation, we will use Akka. So in particular, Akka Stream. So probably if you are listening to this talk, you already know something about Akka Stream, but let me just give some points to make it clear what are the things that I use of Akka Stream in this presentation. So for starters, Akka Streams is a library that enables the creation of even complex computational pipeline, while at the same time providing out-of-the-box back pressure. This means basically that the library will handle the rate of data input that is fed into our pipeline, so that we do not ever end up in a situation where we collect too much data and we basically explode due to an out-of-memory exception. For the context of this presentation, we are not going to go into the detail of Akka Stream itself. The only concept that we kind of want to have in our mind is the definition of flow. So flow is a concept in Akka Stream, which is basically characterized by an input, an output, and a materialized value. You can think a flow as a pipe. So you have your input, in this case, the green ball. You put this input inside your pipe, and you end up with some kind of different output. In this case, the ball is now orange. And the materialized value is just some way to interact with the internals of the pipe. So in this case, I represented it as a window that let us see basically this transformation from green to orange ball. Okay, however, this is nice. However, we have a problem if we want to employ flows to implement our microservices, our streaming microservices. And the first problem is that basically the one of one-to-one flows, meaning that Akka Streams are kind of too powerful because they can drop elements, they can duplicate elements, or they can produce elements out of thin air. This means that we do not have any guarantee that when I put an input inside my flow, I don't know if I will ever get an output as a result, or I will get multiple output as a result. So this is kind of problematic. And apart from that, they really do not model the context association to the data. So to this last point, actually, Akka Streams provide a kind of built-in solution. and that is a flow with context. And this abstraction basically solves the context modeling problem. Okay, now we can operate on the data without worrying too much about the fact that we have a context, which is the Kafka offset associated to it. However, we are still have a problem because flow with context allows filter or duplication of elements. And on top of that, it restricts usage of reordering operators like stateful map concat and group by. Okay, so now let's see the first thing that Spekka puts into into our plate to solve these problems, and that would be flow with extended context. So this is Spekka's solution to the one-to-one flows. It models flows association to context just like flow with context does, but now it strictly guarantees one-to-one semantics. Now we are sure that when we put an input inside our pipe, we will get one output outside of it. And also, it allows reordering operators. Okay, this is nice. So when I'm talking about flow with extended context, what I have in mind is a picture like this. So we have our input that is formed by the data part and the context part. So the data is the green ball and the context is the purple thingy there. We fed this data into our flow with extended context where we do a fan out operation. Then we have a different processing step into the different branch of our fan out. But at the end, we produce all the same type of output. Then we collect back with a fan-in operator and we end up with a result. And this result is a list multiple output, but still associated to the same context that we had in the beginning. Okay, so now let's go and try to play a little bit with flow with extended context. But to do that, we need to define some kind of domain. And since in this day and age, superhero movies comes out like once every 3 seconds, I think that they make a good example of a domain. So here it is, the big superhero stream. Basically, this will be our domain. We will be working with movies. They are characterized by a title, a list of actors, and they exist in one universe, which can be either Marvel or DC, and they have a duration in minutes. Okay, so our objective is to build a program computing the rolling total duration of the movies in the stream. This sounds easy enough. So with flow with extended context, we could do something like this. So we define our movies duration flow. We use a flow with extended context that takes a movie as an input and carry on a generic context CTX. And we use the operator stateful map. This is really similar to stateful map concat of base Akka flows, Akka Streams flows. So what we do, we just define a local state, the total duration, and whenever we get a movie as an input, we just increase the total duration and we return it as an output of our flow. Okay, so now if we were to build a program which uses this flow and fed it with a list of movies and massage a little bit the output to be nice and readable, we would end up with something like this. Here, the context is just the index of the movie inside the array of movie that I used to create the source. So we can see that we have a bunch of movies and that we can see that our output, the total running duration, increases with each and every movie. This is okay, nice. We did something, nothing really special. We could have done exactly the same with normal Akka Streams. So what gives? Well, now management comes in and say, well, this is not really what I wanted to do. I would instead like to do this total running computation by grouping by universe. Okay. So sounds easy enough. We could go back and change the definition of our flow by keeping 2 local states instead of 1. But instead, let's see how we can go another way. So let's use Spekka's partitioning tree support. So here how we would go about that. So we define a movie's duration by universe flow, where we use Spekka's partition tree builder, and this will create a partitioning trees that takes movies as an input and again carries through this generic context CTX. At this point, we are branching using the universe of the movie as a key. And then we are gonna build the leaves. So basically in this build function, we are given the keys from the leaf to the root, and we can use them to build a flow. In this case, we are just reuse the same flow that we defined previously, our movie's duration flow, and we just attach the universe to the output to make it a little bit more readable. So if we were now to run our program with this definition, we would end up with this kind of output. So again, we have the context, the movies, and now we can see that whenever we switches from the movies in the DC universe to the movies in the Marvel universe, we actually restart also the computation of the total running time. Okay, you can say, nice, I could have done exactly the same using Akka's group by, but whatever, it's nice. Okay, but again, management comes in and say, well, this wasn't really the objective. The actual objective was to do this computation but grouping it by actor and universe. So you could say, well, it's kind of the same thing as before, but if we actually think about it, it's different, because before we had that one movie existed only in a single universe, but now one movie has multiple actors. So we are not really talking about partitioning the data. It's something a little bit more tricky. It's something that standard Akka group by or partitioning directly into the Kafka queue wouldn't actually help us to solve. So again, let's see how Spekka's partitioning tree can help us here. So again, we build a partition tree that takes movie and carries through a context, a generic context CTX, but now it's something different. Now we do this multicast partitioning, where we basically are given the movie and we need to return the set of branches that we want to feed this movie to. Okay, you can actually see that there you have a second parameter, the underscore, and that parameter would be the set of currently existing branches for this level of the tree, meaning that you could use that second parameter also to implement a broadcast, but that only broadcast this input message to things that were already instantiated before. Okay, after that, we basically do the same stuff that we did before. We partition by universe, and then we build our leaf. And in this case, you can see that now we have two keys. We have the universe that exists, that the movie exists in, and the actor, the single actor that we are talking about in this leaf. And we can build our flow. An interesting point now is also to mention that those universe and actor are actually typed. So we didn't lose any type information in doing partitioning, and we can exploit those into our program. So again, here we do the same thing. We reuse the original flow implementation, and we just attach the actor and universe so that we can actually read the output. So if we use this definition of the flow to run our program, we would end up with something similar to this. Now you can see something different. The outputs are now lists. This is because obviously we did a multicast operation. So a single input now results in multiple outputs, but we wanted to keep the reference to our context. This is the really important point to get one-to-one flows. And so we can see that, for instance, in the case of the context 0, Man of Steel, we only have a single result. There is Henry Cavill with the duration of the movie in the DC universe. But then for Batman versus Superman, we have both Batman, Ben Affleck, and Superman, Henry Cavill. And now we have the two distinct results. Okay, and then we can also look at the only special case that is Ryan Reynolds that exists both in the Marvel universe and DC universe. So Context 2, Green Lantern, Ryan Reynolds for the DC universe, and Deadpool, Context 7, Ryan Reynolds in the Marvel universe. Nice, he's the only one that can do this. Okay, next. So now that we have seen a little bit what flow with extended context can do, let me show some other interesting operators. So the first one would be ordered. This is an operator that you can use to ensure that the order of the output of your flow is consistent to the ordering of the inputs. All of this while maintaining back pressure. When would this be useful? Well, imagine that in your flow, you want to implement some kind of asynchronous operation. So at some point, you take some input and you call some external service that returns a future, so result can get out of order. Well, using this ordered operator, you can ensure that at the boundaries of your flow, everything will remain in order. And then, since we now have one-to-one flows, and we can also ensure ordering of these flows, it means that we can safely zip them together. So if we have two flows that start from the same kind of input, we can actually zip them and get a flow that starts from that input, but end up with a tuple of the results of the tuple of the output of the two flows. And then we have this strange via multiplexed operator. And here the idea is that if you have a flow that returns an iterable of results, so in this case, flow 2 returns an iterable of B, and you have another flow that goes from B to C, you can use this flow, so flow 3, and apply to all the elements inside the iterable of the first flow, so flow 2, getting as a result basically a flow that starts from the same input but ends up in an iterable of the output of your second flow. And lastly, you can see how using and interacting between Akka Stream and Spekka is kind of easy. You can see there that the only thing that you need to do when you have the standard tupled representation of data and context is just to wrap your context into an extended context. And at that point, you can use the usual via operator to attach a flow with extended context. And then at the end, if you want to take out your context and re-get your data and do something else, you can just call the inner context on your extended context object. Okay, so this is nice. At this point, we have seen that Spekka introduces something meaningful, but we have a problem. We still have no way to interact with the state of our flow. We have no way to ask our flow for what is your current duration right now. Okay, so Spekka helps us by creating a different model for stateful flow. And this model is built on three main concepts. The first concept is the logic. This defines what the flow actually does. Then and the logic can be even base or durable state. So even base, if you want to do even sourcing, durable state just means that you are actually changing the state at every step. And it can be either sync or async. Then you have the backend. And the backend defines how the logic is actually run. And finally, you have the registry. This is like analogous to the actor system, and it basically handles the life cycle of the stateful flows. So now, let's see how we can use Spekka stateful flow to revisit our program. So we start by defining our command. So we want to support a single command, and this command is, please get me the current duration of the running total duration. And since we are in Akka land, we will use actor refs as a mechanism to send back a response. then we can actually start to define the logic. So here we are going to define a durable state logic with a bunch of type parameters. They are basically, the first one is the internal state that we are going to store in the stateful flow. The second one is the type of the input of our flow. Then we have the output, and finally the type of command that we want to support. So what we need to do is to define the initial state. So every time that our flow is instantiated, we want to have an initial state. And in this case, we want to just start from 0. Then we need to define the stream processing function. That is what we are going to do when we receive an element from the stream. So we are given the state and the input, and we need to define our processing. So similar to what we have done in the beginning, we are just taking the state, the current total duration, and we sum the duration of the movie in input. And we get an updated duration. And then we use this updated duration to return a processing result, which is basically contains the new state and also one or more outputs. In this case, we use the same thing, the updated duration, both as the new state and as the output that we want to produce. And next, we define the handling of the command. So again, here we are given the state and the command. And here we just have one single command that we want to implement. And so we say that whenever we get the get current duration command, we just reply to the actor ref with the current duration, so with the state, and we return as a processing result the state itself. We didn't change anything, so we just return the same state. And notice that for commands, there is no support for producing outputs. Okay, outputs of the flow. Okay, so here is the logic. Now we can go to the next step, which is the backend selection. So in this case, we are going to do something simple, and we are just going to use an in-memory implementation of the backend. And whenever we select a backend for our logic, what we get is something that is called a props. And this is basically a complete description of our stateful flows. It's described what are the stateful flows does and how it runs. Okay, nice. So we just are missing a single step, that is the registration. So in the registration, what we can do is, well, first we need to create a registry. And as I said before, the registry is kind of analogous to the actor system. So usually you only have one instance in your application. And once you have the registry, you can actually register the props that you get when you selected the backend by giving it a name. This will be the kind of entity type of the flow. And when you do this registration, you get as a result a builder. This is something that you can use to actually instantiate the flows. So let's see how we can use this builder to change our program. So again, as before, we have our partitioning tree. We do the multicast partitioning, then the standard partitioning for the universe, and then we are at the leaf. We need to build the leaf. So now we do something kind of different. First, we need to come up with the entity ID of this leaf. And in this case, the entity ID is just the actor and the universe. So this would be like the key in our database if this state would have to be saved there. So this is where we would have saved the data for this leaf. And once we have the entity ID, we can use the builder to ask for a flow with extended context that operates on that entity. And then as before, what we do is to just attach the actor and the universe to make the output readable. But actually see that here there is something different. We are doing a double mapping, and afterwards we are doing a flattening. And why is this? This is because by design, Spekka stateful flow produce always a sequence of output. This is because we have said that flows cannot filter results. They cannot produce multiple results because we want a one-to-one representation. But here, in stateful flow, if we want to support the fact that we do not want to produce any output for an input, or we do not want, or we want to produce multiple outputs for an input, we need some way to do it. So basically, all the output of a stateful flow is always represented by a sequence of results. And this is where the via multiplexing operator that you see previously comes actually into play, because it simplifies working with this kind of environment where you have a list of results and you can apply a flow to that. Okay, so if now we were to run our program using this flow definition, we would end up with exact same output that I showed you before. So there is no sense in showing it to you again. But we have actually gained a new feature. Now we can interact with our flow. So we can use the builder to ask for a control interface, and we can use this control interface to command our flow. And in this case, we are commanding, expecting a result of type integer, the duration, the current rolling duration. And we are going to ask the entity and recaval DC for the current duration. And since, again, we are in Akka land, what we end up with is a future. So when the future is completed, we can actually go and produce some side effect. In this case, just print it to screen. Probably what you want to do in this case is to complete some Akka HTTP route. Okay, this is now it starts to become interesting. We have some features that are worthy, but we still have to think about one problem. And that problem is side effect ordering. That is, anytime that we interact with the outside world, we are doing a side effect. And we want to control when this side effect happens with respect to our state saving. And side effect in this case could be, I want to write into a Kafka topic. I want to change something on the database. Okay, so how can we approach this problem? Well, in Spekka, anytime you have a processing function, you can specify some side effect that you want to process, to perform. And you can ask them to happen before the state is modified or after the state is modified. And here is how you would go about that. So in this case, we have a durable state processing result where we change the state, we return an updated state and some output. And then we can say, okay, I also want that before that updated state is persisted, I want these before update side effect to be performed. And notice that these inside these before update side effect, we basically end up with an at least once semantic. Instead, if we were to say, okay, apply this side effect only before, only after the state has been persisted, we would end up with at most one semantic. And this is tied to what I was talking about in the beginning of the ordering of the operation. As I said before, if you were to do a side effect only after the state is updated and your program crashes, you will get back that same message thanks to the durable queue, thanks to Kafka. But at this point, your state is different. So there is no guarantee that you will produce the same processing results, so the same side effect. So bear in mind, if you want to have at least once, you need to perform your side effect before changing your state. Okay, nice. However, we still have a problem. Our state is still transient. That means that if we restart, we lose everything. Okay, here Spekka actually comes to our help by providing some implementation of stateful flow backend based on Akka persistence. And we have an implementation for event-based flows that uses the event source behavior, and for durable state flows, which uses the durable state behavior. And here is how you would actually use those. Basically, let's say that you have an event-based logic. So what you can do is to just select the Akka persistent stateful flow backend by specifying some kind of storage plugin. Here you can see that via code I specified that I want Cassandra. You could have also used some kind of configuration base, so not be required to specify it by code, but I like the code way better. And then you can actually specify what's your event adapter, snapshot adapter, and even events partition if you want to use Akka projection later. Obviously, you are still responsible of providing the serialization. So you need to configure the Akka serialization for your adapted events and snapshot. But if you use protobuf, it's basically free, so go for that. And you can see that the same can be said for durable state. Again, there is an Akka persistent stateful flow backend for durable state. Same idea of selecting the persistence plugin. And in this case, you only have the snapshot adapter, as we don't ever talk about events in the case of durable state. Okay. Nice, but we are not done. We still have a problem, and that is that our flow is not yet scalable, meaning that the more movies that we process, the more actor we learn about, and at some point we will run out of memory and crash. Okay, so what's the solution of Spekka here is an integration with Akka cluster sharding that transparently distributes your stateful flow on a cluster. Actually, what gets distributed are the entities flows responsible for a single leaf in a partition, let's say something like this. And how can we use this support for Akka cluster? Well, it's really simple. Let's say that, again, you start by defining a registry, just as we did before. Then you initialize your cluster sharding extension of Akka. And we, in Spekka, we always use the typed variant of Akka. So that's why we use the two typed on the system. And then we can create our sharded registry. And this is just something that takes the base Spekka registry and the cluster sharding extension. And at this point, we can use this new sharded registry to register our flows. And we get back a builder. And this builder have exactly the same type of the normal builder. So basically, we do not need to change anything else in our code. We just need to change the registry which we use to register our flows. And automatically, these pass from local to clustered. Okay, so in conclusion, I hope that in this presentation, I was able to show you that Spekka helps you build effectively once stateful, sharded streaming microservices. And if not, at least I hope that I made you a little bit hungry for Speck. If you want to have a look at the project website, you can see it there. I really want to thank Thinkin, my former employer, for having sponsored my work on this library. It wouldn't have been possible without their support. And I also want to thank Commerce Tools for letting me slack on my onboarding week and coming here to talk to you about my open source work. And now, if you have any question, maybe not regarding the Akka license change, because I know it's a bummer, but I can't do anything about it. I'm here for you.
Hey, Andrea, thank you so much for your talk today.
Thank you.
We have a question that you might have already covered within your talk, but what's the advantage of the state flow versus an actual Akka cluster? What about sharding, rebalancing, passivization, etc.?
Yes. Well, the advantages is basically at the end, we are really using just standard actors on an Akka cluster. But the advantages that you get is that you don't need to talk actors. Actors are really a low-level implementation details. In this way, you can stay into the Akka Streams world, which is a little bit nicer to use. The question about sharding, rebalancing, passivation, well, obviously we are using Akka cluster underneath, so all the things that you would have to do to configure your Akka cluster implementation, you would have to do also here. That's obviously an area where there needs to be more work on Spekka in order to make it better. But you have the same kind of problem, because at the end of the day, what is happening is that you have actors, clustered actors, and we are using cluster sharding. So same problems apply.
Great. Thank you so much. I don't see any other questions right now, but if any more come through, we'll let you know, and hopefully folks enjoyed your talk as much as the team here seemed to, and congratulations on a great project, and thanks for being here.
Thank you very much. It was my pleasure.
Fire in retro rock.
Roger, Matt. Ready to eject.